Okay, what we're going to talk about today is measurement and a concept called tolerance. When we deal with measurements in chemistry, it's very important that we learn to take the measurements correctly so that if you were to, for example, go to college and take college chemistry, you already know how to take measurements. So when you do your college labs, that's something that you don't have to learn. You're already ready to go. Perhaps on a little bit more of a wider scope, if you actually become a scientist, taking measurements is going to be your job. So it's pretty important that you know how to do it right. This is also an important idea for things like construction. So if you've taken any of Mr. Peterson's classes, I don't know if he talks about this specifically, but everything that you measure different boards with or something that you're going to cut out, that measurement that you take, it has to be right, and it has to be to within a certain plus or minus area of what you're shooting for. Has anybody taken Mr. Peterson's classes? Does he talk about this idea that tape measures? Does he talk about having to get it like really close within certain give or take on either side? It has to be right.
Here in carpentry or building trades.
Building trades. So if you're actually going to build a house for somebody, this becomes really important. And usually engineers will talk about this in kind of a plus or minus point value. You have to be within this target range, plus or minus so much. We deal with that in chemistry too. We call it a little bit different. We call it tolerance when we deal with it in chemistry. But that's what we're going to learn how to do today, how to take measurements correctly based on the piece of equipment that you're using. So here's our quick little example. You have a ruler. Measure your piece of paper. We're going to go ahead and measure in inches because that's what everybody's most familiar with, even though we usually use centimeters in science. Measure the length and the width of your piece of paper and write down your measurements. So what are we getting for the length of the piece of paper? You can just tell me. 11. 11 exactly, right on the nose. Did anyone get just above or just below 11? Not today. We must have pretty good rulers. So we'll put 11 inches. How about the width? Ellie? 8.5? Anybody get something different than 8.5? How many of you said it must be 8.5 because that's what I know it should be? A couple. Okay, we'll put 8.5. Usually I get a couple of people who say that it varies just a little bit. We must be right on this morning. So taking these measurements, you have compared the measurement that you actually got, which we would call a physical quantity. The measurement that you actually got is a physical quantity. That's what you physically measured. And you compared this, probably without even thinking about it, to what you know to be true about that piece of paper. So this would be a known standard. You know that that piece of paper is supposed to be 8.5 by 11. Probably this gave you a little bit of bias in your measurements. Probably you looked at the measurements and went, well, I know it's supposed to be 8.5, 11, and that's pretty close, so I'm going to call it 8.5 by 11. This is one of the things that we tend to do with our measurements in chemistry as well. We'll have some known standard that we're going to see how close we can get during a lab or during an activity. And the overall point of this, and again, I'm a little surprised nobody got just above or just below, but the overall point of this was to show that different people can measure things differently, so that what one person might call 8.5, the next person might call 8.4. And we all got the same answer apparently, so the little illustration didn't work as well as anticipated, but right down here where these two little dashes are, we're going to put what was the idea of this demonstration, or what were we supposed to have seen? The idea for this, again, we were supposed to get some variation here, was that we have to measure as precisely as possible without misrepresenting what our instruments can do. We have to measure as precisely as possible without misrepresenting what our instruments can do. If you take a look at that ruler that you have, would it be correct to measure the width of your paper, which we know was about 8.5, but would it be correct to make up a whole bunch more numbers? In other words, I'm going to measure it with my ruler and I'm going to say it's 8.563478.9. Do you have any way of knowing that those numbers are correct based on the lines on your ruler? No, most of you are shaking your heads no. That's what we're trying to get at here. We have to measure as precisely as we can. We have to get the best measurement we can without misrepresenting what our instruments can do. If I just make up a whole bunch more numbers and list them on the end of my measurement, I'm misrepresenting what my ruler can do. My ruler doesn't measure that small, so I can't have that many numbers. Does that make sense? You guys are all afraid of being the live studio audience, aren't you? Okay. I'm going to scroll down here and erase the writing. And we're going to talk about this idea a little bit more specifically, and we're going to call this idea tolerance. The tolerance of an instrument tells you how precisely that instrument can be used. And let's give it an official definition up here where it says tolerance. The tolerance of an instrument is the smallest divisions, and by divisions I mean lines, so the smallest set of lines on an instrument that can be expressed or written as a power of 10. The tolerance of an instrument is the smallest divisions on an instrument that can be expressed as a power of 10. What does that mean? If we're going to figure out what this definition means, the first thing we might need to understand is what's expressed as a power of 10? If you've got some space maybe just above this in the margin, I'm going to put just a couple of examples of what does it mean to have it expressed as the power of 10. So let's list some powers of 10. If I had, and again, hopefully you're writing above this somewhere because I'm going to erase this in a second. If I had 10 to the first, what's that number? Anything to the first is Should I start with a smaller one? How about this one? 10 to the 0 is?
10.
Not 10. 1. Anything to the 0 power is 1. Anything to the first power is
10. Well,
itself.
10,
So
yeah,
this would be
so
10. Okay, maybe this one would be easier. What's 10 squared? 100. What's 10 to the third? 1,000. All of these numbers right here, 1, 10, 100, and 1,000, those can all be written as powers of 10. 10 to the 0, 10 to the first, 10 squared, 10 to the third. We could keep this list going and get our numbers bigger. Or we can keep it going in the other direction and make it smaller. If I wanted to write 0.1 as a power of 10, do you know what that would be?
10 negative 0.
Oh, you're close. It would be 10 negative 1. 10 negative 1. If I wanted to write then 0.01 as a power of 10, that would be negative 2. 10 to the negative 2. Any of these numbers here can be written as a power of 10. 0.01, 0.11, 10, 100, 1,000. Any of these can be expressed as a power of 10. So the tolerance is the smallest set of lines on an instrument that fits into this list. That could be a power of 10. Let me ask you a question. Can I write 5 as a power of 10? No. Can I write 7.5 as a power of 10? No. Can I write 20 as a power of 10? No. The only things that are powers of 10 are in this list. Maybe a rule of thumb would be if a number can be a power of 10, it's probably only got 1s and 0s in it. So anything that doesn't have a 1, just 1s and 0s only, is not going to be on this list. Do we kind of understand that idea? Nod your head if you're with me. I know it's Monday. Okay. I'm going to erase these examples then. And let's look at some examples that have a little bit more concreteness to them. Let's start with the very top one. It's supposed to be a ruler. These horizontal ones are supposed to be rulers. So let's say we would like to measure a pencil. And I'm just going to draw the end of the pencil. Here's our pencil. It continues off to the left. Here's the lead. There's where it's sharpened. Pencils usually have lines down the side. Now we need to take a measurement of that pencil. Right there. What is that? If you had to estimate what that measurement is, what would you say? Just give me a number.
14.
14. How'd you decide on that number, Grace?
Because it's a little less than half.
Perfect. It's a little less than half. I probably agree. I think 14 would be a pretty good estimate. Do we know it's not 13? Do we know it's not 13 and a half? 13 and 3/4? 14 and a quarter? We don't know because we don't have enough lines. 14 is about the best we can do, and that's because of the tolerance of this instrument. So to determine the tolerance, which helps you figure out what your measurement's going to be, look at what your ruler or your piece of equipment counts by. What does this one count by? 10, 20, 30. Counts by tens. So, was 10 on our list? Yes. That means 10 is a power of 10. Or it could be written as a power of 10. So the tolerance for this instrument is 10 centimeters. What that means is that when you take your measurement, you could be anywhere plus or minus almost that much. Not quite, but that's kind of the idea that we're getting at. Okay, so our measurement here has got to be, we're going to go with 14. And that's about the best we can do. We don't know if it's 14 and a half, 14 and a quarter, 13 and 3/4. We don't know because we don't have enough lines. The best we can do is about 14. You could write 13. There'd be no way for me to prove you right or wrong. You almost could write 15. You could argue that one a little bit more because you can mark the halfway point. But the point is that this is pretty much the best we can do, to say 14. Let's do that same pencil. Maybe we'll make it just a little bit longer. That same pencil on the next ruler. So there's the pencil. Oh, it's a little bit duller this time. It's been used. And now, trying to take the measurement, the tip of the pencil is right about there. What does this ruler count by?
1.
It does count by ones. 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. This counts by ones. Was 1 on our list as a power of 10?
Yes.
Yes. So the tolerance for this ruler is 1 centimeter. What would you say the measurement was? If you had to estimate, what's that measurement? 10, 11, 12, 13, 14. It's above 14, but below 15. So what would you say?
14.65.
Do you know it's 0.65? What if it's 0.75? What if it's 0.85?
You can't tell.
You can't tell. That's the point. Ha, pencil, point, measurement. What's the best we can do? 14. We know it's point something because we can see that it's in between, but we can't really go too much further than that. 0.65 might be overestimating a little bit because we don't have any smaller lines than this. We could say 0.6. We could say 0.7. We could say 0.5. We don't have enough lines to go any further though. 0.765893. We don't have enough lines for that. So 14.6 is the best we can do, or 14.5 or 14.7. Okay, next one. Now we're doing liquids. Let's fill the graduated cylinder to just about here. Notice the liquid level is curved. This is otherwise known as the meniscus, and you need to read from the bottom. That means we're reading right about, maybe there. What does this cylinder count by? Say it again. 0.1s. This is 5, this is 6. 5.1, 0.2, 0.3, 0.4, 5.5, 0.6, 0.7, 0.8, 0.9, 6. So this counts by 0.1s. Was that in our list as a power of 10?
Yes.
Yes. So the smallest lines that are a power of 10 would be 0.1 milliliters. That's our tolerance. What's our measurement going to be? Let's see. 5.1, 2, 3, 4, 5, 6, 7. We know it's that much. And it's not up to the 8, so we're not going to say 5.8. But it's a little beyond the 7. 1 after the 7? So 5.71? Do you know that it's not 5.72? No. So you could put 5.71 or 5.72. We know it's a little bit higher than the 7, but we're going to have to estimate how much higher. Okay, let's do the last one. Again, this is a liquid, kind of like a graduated cylinder. Read from the bottom of the meniscus. The measurement looks like it's about there. Okay. What do these lines count by? How many are there? 1, 2, 3, 4, 5. There's 5 steps in between 5 and 6. What do those count by? 0.2. If you don't know that, go 6 minus 5. Okay, that's 1. 6 minus 5 is 1. And then divide by how many steps there are in between. 1, 2, 3, 4, 5 steps in between. You get 1/5, which is 0.2. So this is counting by 0.2s. Is 0.2 on our list? No. So even though we have lines that count by 0.2s, we can't use them for the tolerance because it's not on our list. That means we need to go to the next biggest set of lines. So the next biggest set of lines is from here to here. What does that count by? 1s. Is that on our list? Yes. So the tolerance is 1 milliliter. And I'm going to erase this little example down here. Now let's leave that for just a second. We're going to come down and fill in our golden rule, and then we'll go back up and do our measurement for that last one. The golden rule for tolerance says, always estimate 1 digit passed, or 1 place passed, the tolerance of an instrument. When you're taking your measurements, you always go 1 place past the tolerance of an instrument. In other words, what we've been doing this whole time is read between the lines. One place past the tolerance. I'm going to put a little note here off to the side. I hope we still remember our place values or our place numbers. So in other words, if I had the number 100, what's the place called where the one is? Hundreds. What's the place where the first 0 is? Tens. We all learned this in elementary school, right? Mm-hmm. What's the next one? Ones. And then tenths. Okay, this is kind of important because of our rule. Always estimate 1 digit past the tolerance. If you were to look at this example here where the tolerance is 1 centimeter, the tolerance for that one would have been in the ones place. And if you look at our measurement, we estimated to the tenths. We went 1 place past. Same thing if you look at the first one we did. The tolerance was 10, so the tolerance was here in the tens place. Look at our measurement, we estimated to the ones. Now if you look at this last one that we still have to finish, where's the tolerance? What place? The ones. So we should, that's interesting. Whoops, there we go. We should, tolerance is in the ones. We should estimate to the tenths, but no further. Okay, so look at our measurement again. 5, 5.2, 5.4, 5.6. Here's 5.8. It's not 5.6 because it's above it. It's not 5.8 because it's below it. 5.7
Yeah.
milliliters. And we can't go any further than that. We might think we know that we can go further, but we can't go any further because that's where our estimate place is after the tolerance. All right, that is it for today.